And hello and welcome to lesson 43 of my DP chemistry curriculum. Today we're going over structure 2.2.6. Molecular polarity depends on both bond polarity and molecular geometry. So we're going to be able to deduce the net dipole moment of a molecule or ion by considering its bond polarity and molecular geometry. We'll go over some examples and we'll include species in which bond dipoles do and do not cancel each other. So we'll explain what that means as we get going. So, with that said, to talk about molecular polarity, we should start by considering CO2, carbon dioxide. And you need to be able to draw the Lewis structure to really determine polarity, but it looks a bit like this. Now, if we recall from our last lesson and we discussed bond polarity, we found that oxygen, being the more electronegative species, becomes partially negative, with carbon becoming partially positive here. If we are to draw the bond dipoles, we notice two equal length dipoles going from carbon towards the oxygen. So this is our molecule CO2. We have two partially negative ends and a partially positive end. When we look at the word polarity, we defined it before as having two oppositely charged ends. And that's why we have these two dipole moments. We have positive, negative, but we have positive, negative. So we got to ask ourselves a few questions. The bonds are polar. We know that. But what else might be polar? Well, first, let's look at the geometry. So our geometry of this is going to be linear. So this exists as a line with a negative end, and kind of a positive middle. So when we look at this whole molecule, is the molecule polar? And that's the question we have to answer. Well, once again, let's go back to our definition. Two oppositely charged ends. Well, as a line, it has two ends, 1, 2. If I divide it down the middle in almost any way, except for directly this way, we look that one end is negative, one end is negative. CO2 is not polar. So this molecule, while having incredibly polar bonds, the overall molecule is not polar. What we say is there is no net dipole moment. So now comes the part where we look at dipole moments. Net generally refers to the sum. So if we sum our two dipoles, which are vectors, we take one and we add it to the other. And we notice that if we superimpose these dipole moments, they cancel out. So the sum of the dipole moments is 0 net dipole, meaning the overall dipole of this molecule does not exist. And that's how we know that this whole thing is non-polar. So we know CO2 is a non-polar molecule. We can look at it through the definition, having two opposite charged ends, which it doesn't, or we can sum our dipoles knowing that they go forwards and backwards. Quick point of order for physics, if you are just adding two vectors, you just go point to tail, and this is your net vector. So that's how I added two dipoles down here. Anyways, scooching out of that physics, let's look at a different molecule. Let's look at HCl. HCl, on the other hand, has a partial negative charge, a partial positive charge, and this molecule only has one dipole, which means that the bond dipole is equal to our net dipole. Also, the fact that we have a net dipole means that this is a polar molecule. The existence of that net dipole gives this thing polarity. We have our negative side and we have our positive side, and therefore this is a polar molecule. Now, we can always take molecules and add dipoles to figure out whether they are polar or not. So let's go ahead and look at a different example. Let's look at ammonia, NH3. NH3 has three dipoles that we can tell: positive to negative, positive to negative, positive to negative, and these are all the same. If you were to superimpose these, you get forward, back, and then up, giving us a net dipole of up, pointing towards our bonds. So we would say this is polar. But the thing we actually have to consider is that now that we are looking at a overall molecule, this is a three-dimensional shape. And therefore, these dipoles don't necessarily cancel that same way. Ammonia looks a little more like this, and I'm going to use blue for the nitrogen and red for the hydrogen. And I'll use yellow for our electron pairs. So this is our trigonal pyramidal shape. And because of that, we have our net dipoles kind of like the legs of a tripod on like a camera stand or something like that. And so our overall net dipole is actually just straight up, and it's quite large. And so we still can see that this is a polar molecule. So this net dipole tells us whether or not it's a polar molecule. We do have to look at these in 3 dimensions. But because we can just add up dipoles, there's a different way to figure out molecular polarity, and that's via symmetry. Symmetrical molecules, but they must be symmetrical across all planes. Symmetrical molecules are nonpolar because all their net dipoles will cancel out. So a good example is CO2. This is symmetrical. Across every axis of symmetry, it is exactly the same. No matter how you divide this, if you go through the middle, you will get a perfectly symmetrical molecule. However, asymmetrical molecules are polar. And when we look at ammonia, while we have symmetry across this vertical plane on the 2D shape, across any other plane, we do not have symmetry, and therefore this whole molecule is polar. We can look at a couple examples of symmetrical. So let's look at nonpolar or symmetrical. So boron trichloride, and I'm going to just draw the skeletal structure because I don't want to draw the lone pairs. This is symmetrical. It is nonpolar. We already saw carbon dioxide, but maybe like methane. Carbon tetrahydride, which is just methane, is also symmetrical. Even in the 3-dimensional shape, this is symmetrical. And I will show you that in a moment. If we look at some asymmetrical, so some polar or asymmetrical, we have examples like our HCl. We have another example like carbon or dichloro dihydro or carbon dichloro dihydride, or you know what, that doesn't make sense. This is oh gosh, I'm just mixing this one. Monochloromethane or chloromethane. There it is. I can remember my organic chemistry. So in this example, we have a polar molecule. We can make it polar as well by putting the CO there. So before I end this video, I want to talk about why it's so important to look at 3D structures, because these are all 2D. What if we have the molecule dichloromethane, but you were to draw it a little different? In the 2D space, this is symmetrical. However, we can start drawing things in what's called the stereochemical formula, which is 3D. So we use two different lines. So this means in front of page, so like coming out of the page, and this is behind page. So we can redraw this, and we'll redraw it in what we call the stereochemical formula, which is all about 3 dimensions. And we draw our carbon, and we're going to make these bond angles 109.5 approximately. And we have chlorine, hydrogen. Then we have a chlorine coming out in front and a hydrogen coming out behind. And when we look at it in 3D, we can see that the front part of the page, what's coming out in front of the page, is going to be negative, and the parts coming out behind the page are going to be positive. This is all partial negative. This is all partial positive, and the page kind of acts like a divider that separates the positive from the negative, and we find that this is polar. I'm going to show you another example in just a moment, so I'm going to pause it and we'll be right back. So here is a website called Molview, MOLVIEW.org. You can put any molecule in it, and it shows the three-dimensional shape. So the green represents chlorine, the white represents hydrogen, with the gray representing carbon, and it looks symmetrical. We have the chlorine above, the hydrogen to the right and left, but we can rotate and see in 3 dimensions that this is in fact not symmetrical. So this is how these molecules actually look in 3D, and we can see that right down the middle right now we have an axis of asymmetry, where the right side becomes partially negative, the left side becomes partially positive, and this molecule is therefore asymmetrical and therefore polar. So it's going to be really important for you to understand your molecular geometry as well as how to visualize these shapes in 3 dimensions, because just drawing them on a page is not always suitable to determine symmetry. Anyways, I hope this helps, and have